Hello guys, welcome to the video on probably approximately correct PAC learning. PAC learning is all about understanding the relationship between probability, hypothesis space and training examples. Speakers in this video are myself, Saksham Wane, and my friends and classmates Kijan Longren and Shivansh Kumar. All three of us are students of MTech Computer Science at IIT Patna, batch of 2024. In this lecture, we will explore probably approximately correct or PAC learning. PAC learning is a fundamental framework in machine learning theory. The goal of PAC learning is to develop a theoretical foundation that relates four key aspects: the probability of successful learning, the number of training examples needed, and the complexity of the hypothesis space, and the accuracy of the approximation to the target. Additionally, we consider how the training examples are presented. PAC learning seeks to answer a critical question: how well can we learn a function given limited training data? Before diving deeper into PAC learning, let's define some fundamental terms. First, the instance space, denoted as X, represents a set of all possible examples. The concept space C includes the set of all valid target functions that define the correct classification. Finally, the training set denoted as S consists of labeled examples, where each input is mapped to its corresponding output. A key assumption in our analysis is that both the training and testing examples are drawn from the same probability distribution B. This assumption ensures consistency in learning. The primary objective in PEC learning is to find a hypothesis H from hypothesis space that closely approximates the unknown target function f. We evaluate the performance of our hypothesis on new, unseen examples drawn from the same distribution D. The key challenge is to ensure that our hypothesis generalizes well, meaning that it correctly classifies not just the training data but also future examples. Let's consider an example to understand hypothesis learning better. Suppose our target function f is a conjunction of several Boolean variables, while our hypothesis h is slightly a different conjunction. If a variable appears frequently in positive training examples, the hypothesis might include it, even if it is not actually part of the target function. However, if the variable is irrelevant, its impact on classification error is minimal. This highlights a core aspect of learning, making approximation that generalizes well while minimizing errors. In PAC learning, we measure error as the probability that a hypothesis misclassifies an example compared to the true function. A lower error means better generalization. Our goal is to minimize this error while ensuring that hypothesis remains computationally feasible. A common example in PEG learning is learning conjunctions, where the target function consists of logical AND operations. Consider a scenario where a conjunction includes a literal Z. If this literal appears in our hypothesis but not in the actual target function, it may lead to errors. The challenge is to balance accuracy while avoiding unnecessary complexity in the hypothesis. The hypothesis space H is set of all possible hypotheses the algorithm can select. The concept space C is the set of all possible target functions. Typically, the hypothesis space is larger than the concept space. While a larger hypothesis space increases expressiveness, it also makes learning harder due to overfitting. On the other hand, a smaller hypothesis space is easier to learn but may lack the flexibility to accurately model the target function. Thus, there is a trade off between expressiveness and learnability. We define the error of a hypothesis as the probability that it disagrees with the target. When sampling from distribution D, this error can be mathematically represented as the probability that Hx differs from Fx. By bounding this error, we can establish guarantees on learning performance. If the probability of an error is controlled, we can ensure that with high probability, our hypothesis remains close to the target function. A fundamental question in PAC learning is how many training examples are needed to achieve a desired level of accuracy. Well, the number of required examples depends on multiple factors, including the complexity of hypothesis space and the desired level of confidence. A key result in PAC learning is that M grows linearly with the number of features and logarithmically with the confidence parameter, ensuring that we can achieve low error with a reasonable number of examples.
Okay, so hi everyone. Today I, Shivansh Kumar, will be presenting on formulating the prediction theory. In this talk, we will explore the theoretical foundations of learning. We'll understand key concepts like PAC learning and we'll discuss how hypothesis complexity impacts generalization. So let's get started. So, prediction theory is the mathematical framework that helps us understand how well a model can learn from the data and can make accurate predictions. It's important because it allows us to measure how much training data is needed and how well a model will generalize to new and unseen data. Without prediction theory, we wouldn't have a structured way to evaluate learning algorithms. So, now let's talk about the key components of prediction theory. So, to understand prediction theory, we need to define some key components. The instant space X represents all possible inputs, while the output space Y contains all possible labels, such as -1 and +1 for classification tasks. Probability distribution D is unknown but determines how data points are distributed. The training set S consists of M different examples drawn from D, and finally, the hypothesis H is a function that maps inputs to outputs. These elements together form the foundation of learning models. Let's now talk about true versus empirical error. What are these two actually? So, when evaluating a learning algorithm, we differentiate between true error and empirical error. True error, which is often denoted by error D, measures how well the hypothesis generalizes to new or unseen data. It's what we ultimately care about. However, since we only have a limited data set, we compute the empirical error, which is also denoted by error S, which is the error observed on the training data. The goal of the prediction theory is to minimize the gap between these two errors. Okay, so this was all about true and empirical error. Now let's move on to the next topic. So the next topic is probably approximately correct learning, that is PAC learning. So a PAC learning is a framework that ensures that with high probability, which is often denoted as 1 minus del, we find a hypothesis with an error of at most epsilon. This means that even if we cannot perfectly learn a concept, we can guarantee that our model will be probably approximately correct. The key assumption in PAC learning is that both training and testing data come from the same probability distribution. And then let's talk about PAC learnability. A concept class C is said to be PAC learnable if given enough training examples, we can find a hypothesis that has a low error. For PAC learning to work, the number of training examples M should be a polynomial in terms of 1 minus epsilon, 1 minus del, n number of features, and the size of the hypothesis space that is denoted by H. If the hypothesis can be computed efficiently, then the learning process is said to be efficiently PAC learnable. So our next concept is Occam's razor principle. It claims that the smaller hypothesis spaces are better. If I have to explain it to you briefly, then it states that a simpler hypotheses are better. In prediction theory, this means that if we have a smaller hypothesis space, we need fewer training examples to achieve good generalization. The probability that a bad hypothesis remains consistent with the training data decreases exponentially with more examples. This principle is essential when designing machine learning models because overly complex models might fit in the training data well but fail on the new data. Problem of overfitting. So, it claims that simpler hypotheses are better, basically. So, while PAC learning is a useful framework, it has limitations. First, the polynomial space complexity requirement ensures that we have enough training data, but sometimes obtaining large data sets is difficult. Secondly, the polynomial time complexity condition ensures that an efficient algorithm exists, but some problems are computationally hard. Finally, there is a trade off in choosing the size of the hypothesis space. Too small, and we lose expressive power. Too large, and we will risk overfitting. And with this, we will move on to our next topic, that's consistent learners in context of PAC learning. We will explore what consistent learners are, their significance in machine learning, and their feasibility in terms of sample complexity. So let's get started. A consistent learner is an algorithm that finds a hypothesis that fits perfectly well all training examples. In the PAC learning framework, if we have a large enough number of training examples, the hypothesis we choose will be close to the true function. The required number of examples, which is denoted as M, depends on the error tolerance that is epsilon, and the confidence level, that is del. The formula here tells us how many samples we need to guarantee a hypothesis with an error less than epsilon and with probability at least 1 minus del. So let's now talk about the importance of consistent learners. Consistent learners are important because they ensure that the hypothesis aligns with the training data. If the training set is diverse enough, the hypothesis generalizes well to the new and unseen data. However, key challenge is computational feasibility. Even if a hypothesis exists that fit the data perfectly, finding it efficiently is not always straightforward. In some cases, searching for a consistent hypothesis can be computationally hard. If we summarize, then KCNF, K-class CNF, and KDNF are PSE learnable, meaning they require a polynomial number of samples. However, biased learning, that is all Boolean functions, is not PAC learnable due to its exponential complexity. Some representations like KDNF face computational challenges, even if they are theoretically learnable. This demonstrates that sample complexity and computational complexity, both of them must be considered while designing learning algorithms. So now, continuing our discussion on consistent learners, we now focus on computational challenges of learning K-term DNF formulas. While we saw that KDNF is PSE learnable in the previous section, here we will explore why efficiently learning KDNF is difficult and how we can attempt to overcome these challenges. So, a K-term DNF is a Boolean function represented as a disjunction of K conjunctive terms. In simpler terms, it is an OR of multiple AND clauses. For example, in the equation shown here, each T is conjunction of literals. From a PSC learning perspective, the sample complexity results suggest that KDNF should be learnable. However, the real challenge is computational feasibility. Finding a consistent hypothesis efficiently is difficult. The computational hardness of K-term DNF. The main issue with the learning K-term DNF is computational complexity. So that's the main issue with this K-term DNF. It's computational complexity. Even for a two-term DNF, finding a hypothesis that is consistent with all the training data is NP hard. This means that there is no known polynomial time algorithm that can efficiently find an exact consistent hypothesis for all training examples. This creates a major limitation. While K-term DNF are PSE learnable, they are not efficiently PSE learnable. In practice, we may need to resort to approximation techniques rather than exact learning. So, overcoming complexity and enlarging the way to overcome this complexity is to enlarge the hypothesis space. Instead of learning the K-term DNF directly, we can represent it using more expressive hypothesis space such as KCNF conjunctive normal form. This approach allows us to leverage known learning techniques for CNF, but it comes with a trade-off. While the hypothesis space becomes more expressive, it also grows larger, making computation harder in some cases. We must balance expressiveness with efficiency when choosing representations for learning. So, open problems and future directions. Even in these transformations, several challenges are still there. First is handling inconsistencies in training data. In real world applications, training data is often noisy. If the dataset is inconsistent, finding an exact consistent hypothesis becomes impossible. Second challenge is learning in an infinite hypothesis space. PSC learning assumes a finite hypothesis space, but in practice, we often work with infinite spaces. VC dimension and regularization techniques helps to manage this. The third challenge is finding approximate solutions. Since exact learning is NP hard, the research focuses on heuristic and approximation algorithms that efficiently find a near optimal K-term DNF. So, to summarize, K-term DNFs are PSE learnable but computationally hard to learn efficiently. Finding an exact hypothesis is NP hard even for two-term DNFs. Rewriting in a larger hypothesis space such as KCNF can help, but it has its own trade-offs. Future research focuses on approximate learning, handling inconsistencies, and efficient hypothesis selection. The key takeaway is that just because a function is PSC learnable, it doesn't mean that it is computationally feasible to learn. With this, I conclude my discussion on consistent learners.
Hi, this is Kijan, and I will continue with the topic agnostic learning. In traditional PAC learning, we assume that the target function f belongs to the hypothesis space H. However, in real world scenarios, this assumption is often unrealistic. The true function may be far more complex than any function in our hypothesis space. This is where agnostic learning comes into play. Instead of assuming that an exact hypothesis exists within H, agnostic learning focuses on minimizing error, acknowledging that the best hypothesis may still have some unavoidable error. Error in agnostic learning. In agnostic learning, we deal with two types of errors. The true error, denoted as error d of H, represents the probability that a hypothesis H misclassifies a randomly drawn example from the distribution D. On the other hand, the empirical error, error S of H, is the observed misclassification rate on the training data. The objective in agnostic learning is to find a hypothesis that minimizes training error while ensuring that it generalizes well to unknown data. Hoff-Eddings bound and generalization. One of the key mathematical tools used in agnostic learning is Hoff-Eddings inequality, which provides a probabilistic bound on the difference between the empirical error and the true error. The key insights here is that as the number of training example increases, the difference between the observed and actual error decreases. This ensures that if a hypothesis performs well on the training set, it is likely to perform well on unseen data as well, with high probability. Sample complexity in agnostic learning. To ensure that empirical error is a good approximation of the true error, we must choose a sufficient number of training examples M. The number of required examples depends on three factors: the size of the hypothesis space H, with larger space requiring more examples. Second, the confidence level 1 minus delta, with higher confidence requires more examples. Third, the desired error bound sigma, where small error bounds demand more data. This highlights a fundamental trade-off. A more complex model requires significantly more training data to achieve reliable generalization. Agnostic learning versus PAC learning. To summarize the difference between agnostic learning and PAC learning. PAC learning assumes that the target function exists in the hypothesis space H. The goal is to find a hypothesis with an error of at most sigma with high probability. Whereas in agnostic learning, it removes this assumption, acknowledging that the base hypothesis in H may still have some inherent error. The goal is to minimize the overall introduction to VC dimension. Now let's shift our focus to an important theoretical concept in learning theory, the VC dimension, or Webnick-Chervow-Nikas dimension. The VC dimension measures the expressiveness of a hypothesis space by determining its ability to fit various data patterns. This concept is crucial because it helps us analyze the sample complexity of learning algorithms and understand the trade-offs between model complexity and generalization. Shattering, key concept in VC dimension. A hypothesis class H is said to shatter a set of points if it can correctly classify all possible labelings of those points. For example, consider a linear separator in two-dimensional space. It can always separate 2 points, but it may not be able to separate 3 points in all the possible ways. The VC dimension of a hypothesis space is the maximum number of points it can shatter. This provides a quantitative measure of how expressive the hypothesis class is. Examples of VC dimension. Different hypothesis classes have different VC dimensions. A linear classifier in 2D has a VC dimension of 3, meaning it can correctly classify any labeling of 3 points but not necessarily 4. A conjunction of Boolean literals has a VC dimension of n, where n is the number of literals. More complex models, like neural networks, have much higher VC dimensions, indicating greater expressiveness but also increased risk of overfitting. VC dimension and sample complexity. The VC dimension plays a critical role in determining the number of training examples needed for learning. If a hypothesis class H has VC dimension D, then the number of required training samples follows this relationship. It is given by the mathematical expressions. This tells us that models with higher VC dimensions require more training data to ensure that empirical error closely matches true error. It also highlights an important trade-off. More expressive models need more examples to generalize effectively. Sample complexity lower bound. We have discussed the upper bound on sample complexity. How many examples are sufficient to learn? But there is also a lower bound, which tells us the minimum number of examples needed for successful learning. The key takeaway here is that if we have too few training samples, learning becomes impossible with high probability. The VC dimension, therefore, sets fundamental limits on what we can learn effectively.